Hello. Today we're going to be taking a look at this really good physics problem here. It's going to be a one-dimensional kinematics problem. We will be dealing with a couple of our big five kinematics equations. I'm going to read through the problem and then we will solve it together. So, we've got two rugby players that are running towards each other. They are 37 meters apart. If one is accelerating from rest at 0.5 meters per second squared, and the other was already moving at 31 meters per second and maintains her speed, we're going to then solve the following. So before we go through what the question is asking us, I'd just like to highlight that there's a lot of key pieces of information that we've got to extract from this problem, right? And I think first step, what we should do here is just draw out a diagram to get a better understanding. So let's call this our player 1, okay? We can consider this person to be the one who starts from rest and then accelerates at 0.5 meters per second. And then the other one we can call player 2, right? And just say that they're the one who's moving at 3.1 meters per second and maintains that speed. So we also know that the distance between the two of them is 37 meters, right? And what we know is that they're going to be running towards each other. And we want to evaluate kind of the initial state, right? The initial state where they are right here. And then their final state once they collide, right? Let's also set up our compass really quick to state our positive and negative directions. I'm going to say that forwards is my positive direction and backwards is my negative direction. So part A is asking how long before they run into each other. So that'll be the time in which they collide, right? Next, how fast was the accelerating player going? So that'll be this player 1. We want to kind of figure out how fast they're accelerating just before the two players collide, or right at that instantaneous point where they collide. So I'll call this the final velocity of our player 1. And then finally, we also want to figure out how far each player has run. So we can just call this the displacement of our player 1 as well as the displacement of our player 2. Okay? Alright. Finally, just to state what we know, I know that my player 1, right, they have an initial velocity of 0 because they're starting from rest, and then I know that they're accelerating 0.5 meters per second squared in the positive direction based on what I've said, so the forwards direction, this way, right? And then for our player 2, we can just consider that they have an initial velocity, or technically an overall, just a velocity, right? Because they're maintaining that velocity of 3.1 meters per second. And that'll be in the backwards or negative direction, right? I've classified that they're going to be moving this way. We also know that since they're maintaining their speed, right, this person is going to have an acceleration of 0. Okay, now that we've kind of got everything set up here, let's start by solving part A. So how long before they run into each other? So what I'm going to do is I'm going to set up two separate equations and then do some substitution and then solve for the time. So first I'll set up my equation for my first player, and I'm going to use this big 5 kinematics equation here. So the displacement will equal our initial velocity times our time plus 1/2 times the acceleration times our time squared. For our player 1, we know that our initial velocity is 0, so this whole term, velocity times time, will go to 0 since 0 times t, right? We'll just give it 0, so I'll be left with my displacement equals 1/2 times 0.5, which is my acceleration, and it'll be positive 0.5, right? Because I've classified that forwards as my positive direction. And then that'll be times my time squared. And then finally, I'll get a displacement of 0.25 times our time squared. Next, for my second player, I'll use the same kinematics equation. And then for this one, we know that our acceleration is 0, so in this time this term will go to 0. So then I'll be left with my displacement equals my initial velocity, which is negative 3.1, right? Negative 3.1 because I've classified that they're moving in the backwards or negative direction, times my time. One other thing that we need to do for our player 2, when compiling my two equations here, I've considered this location here to be our reference point, okay? So this is technically like reference point 0. This is 37 meters because we've classified that player 1 and 2 from our initial state are 37 meters apart. So what I need to do here is actually account for that initial separation with my second player. With my first player, they start at 0 with respect to how I kind of set up my problem here. So because of that, I can just kind of leave this displacement here. Just a key note that the displacement or the change in, right, this delta here represents the change in our displacement, can actually be represented by d2 minus d1 or df for our final position minus our initial or d1 position or distance, however you want to call it. So for the first player, right, our d1 is technically just 0 because we're starting at point 0, so our delta D is just equal to our whatever D2 is, however far we've traveled. But for our second player, it's going to be a little bit different, right? So if I make a note on the side here, we're going to have D2 minus our D1, and we know that our D1 for our player 2 is 37 meters with respect to our kind of 0 or reference point. So I'm going to need to account for that in this equation that I'm setting up here. So instead of writing delta D, I'm gonna kind of populate this in to say that D2 minus 37 equals negative 3.1 times my time. And then finally, I'd have D2 equals negative 3.1 delta T plus 37, okay? So this is kind of the equation I should be left with. I could technically then just rewrite this as delta D equals 3.1 times my time plus 37. Okay, so now I've got these two equations, and now I'm going to use some substitution. I'm going to get a quadratic equation, and then I'm going to solve for my time. Okay, so, right, I'm just going to set this now equal to this, right? Delta D, they're both equal to each other, so I'm going to be left with here negative 3.1 delta T plus 37 equals 0.25 times my time squared. And then I'm going to rearrange this and set everything equal to 0, so I'll be left with 0.25 times my time squared plus 3.1 T minus 37. So I have some quadratic here, right? In my standard form, I've got A equals, right? I'll typically have ax squared plus bx plus c. So my A term is 0.25, my B term is 3.1, and my C term is negative 37. So I'm going to use the quadratic formula to then get what my time values are. I'm not going to show that work here, but go ahead and use either a quadratic formula calculator, or you can practice that on your own paper there. But in this case, we're going to get a time of approximately 7.45 seconds, or negative 19.85 seconds. And now, when dealing with time with any of our physics problems, if we are in a situation where we're going to use the quadratic formula and get two time values, right? It's important to understand that if we get a negative time value, we can kind of just omit that value because negative time doesn't really exist. So we're going to use this as our final answer and then state that right? For part A, it takes 7.45 seconds for the two players to collide. For part B, I want to find how fast my player 1 was accelerating just before they collided, so that'll be my final velocity. So I can use my big 5 equation, final velocity equals my initial velocity plus our acceleration times our time. So then I'll have my final velocity equals, or my initial velocity for my player A was 0, plus our acceleration, which was 0.5, times my time, which I got 7.45, and that'll give me a final velocity of approximately 3.73 meters per second in the, it's a positive value, so I can say that that's going to be in the forwards direction. Finally, for part C, I want to figure out how far each player has run. So there's a couple different ways in which I could solve this, but what I'm going to do is I'm going to take the two equations that I put together for part A when I first initially found the time, with one minor difference. For my second player, I'm not going to include that plus 37 that I had on the end, and I'll show you why right after we find the displacement for player 1. So for player 1, I'm just going to take that equation and then sub in the time. So I'll get 0.25 times our time, which is 7.45 squared, and that'll give me a displacement of about 13.88 meters, and that's going to be in the forwards direction, right? Because based on my diagram, I've moved from here in the forwards direction to some point here where we collide. So I'll just classify that as my vector. Now for part 2, for player 2, right? The reason why I'm not adding that plus 37 is because I don't care kind of where I'm starting. I just care about that distance that I've traveled. I want to figure out how much distance I've traveled over my 7.45 seconds. So for that reason, I'm not putting in the 37 that I had from part A. Okay? So I'm going to have here negative 3.1 times my time, 7.45 seconds, and that'll give me a displacement or a distance of about 23.1 meters, and that's going to be, this will give me a negative value, so I'll just write the vector in right away and say that it's going to be in the backwards direction. Now, the cool thing is if I take the magnitude of both of these values together, if I add 13.88 and 23.1, we're going to get approximately 37 meters, which is pretty cool. So player 1 covered this distance, right? Player 2 covered this distance, and overall, right, because they were initially 37 meters apart, they've both covered in total 37 meters to the point where they collide, right? So a really good two-object, one-dimensional kinematics problem here. If you guys got any questions or comments, let me know, and I hope this helped.